everybody to our penultimate CAD seminar. Like, I really wanted to use that word in a sentence, so I'm really glad that worked out this time. We have two really good speakers today, Dr. Merret and Dr. Hajj. First, we're going to start with Dr. Merret. He has his PhD in aerospace engineering from UIUC, and he is an associate professor as well. And his research interests include applied aerodynamics, propulsion integration, and configurational aerodynamics. So let's give him a hand, and then we.
Thank you. Thank you for the introduction. I'm here to talk about eVTOL, or electric vertical takeoff aircraft configurational aerodynamics. So first, not everyone may know, I know we got other engineers. If I talk to aerospace engineers, I can skip a couple of these first few slides, but with the mix we have here, I want to kind of give that background of where this all started. So if you go back to the 1940s, we've been trying to do flying cars. Almost since the dawn of aviation, we wanted to do both, right? You think, the Jetsons, for those of us who are in that era, tooling around, pulls up in a briefcase. They tried to do that. Convair did it in 1947. That gives you an idea how far back this technology has tried to go when they've been trying to do it. They had the Taylor Aero car shortly after that, 1949. And there have been attempts on and off for years. Okay. Terrafugia was actually was run by a classmate of mine. They got first flight on this vehicle in 2012. So what is that, about 9 years ago, 10 years ago? They've been working on it, again, about 5 years prior to that. Okay, just to put it in perspective, they shut their doors a couple of months ago. They tried. They tried for almost 15 to 20 years to get this to work. It is a really hard problem to have flying cars. We all want it, right? No one wants to get on I-57 and go to Chicago because it's not only straight and boring, you then hit 294, there's traffic. So you go from wide open space to you hit Kankakee, and then you start picking up traffic until you hit 294, and then you speed up to go around Chicago. We want to get rid of that, right? We want to hop in a vehicle, fly up there in 30, 40 minutes and be done without going to Willard, if we could. Not that Willard's bad. But all of these designs over the years have suffered from a few major flaws. Okay. First of all, these all required runways. That's great if you want to drive to the airport, then take off, then go. If you want to do that and you're here, you can't really go out there anymore, right? And, get on that runway very easily. Okay, so then you got to drive down to Willard. Okay, well, if you're going to Chicago, that's the wrong way. Okay, so that's one of the major flaws with flying cars. Another one is doing that task of driving and flying. Okay, the controls are fundamentally different, right? If you're in an airplane, anybody know how you steer in an airplane? If you're taxiing, you steer with your feet. You don't use the yoke because that's roll. You actually steer with your feet, so it's fundamentally different. You have a different mode that when you're on the ground, you steer with the steering wheel. But when you're taxiing it on the runway, you start with your feet. Again, that's complicated. Don't necessarily want to do that either. Okay. Really, the biggest struggle on all of these vehicles are safety standards. How do you put a bumper on an airplane? I really don't want to be bumping anything, regardless of how hard with an airplane. Okay. They're built so light to be airworthy, they're not set up to take those simple impacts. So do I design an airplane that's now roadworthy? Or do I compromise on the roadworthiness, which we know doesn't work, right? You cut back on your safety standards on cars, problems occur. Okay. These overall size, you can imagine, this is the Convair. They literally took an airplane and kind of bolted to the top. That's not small. Those cars weren't small in general. Okay. You put an airplane on top, it's not much smaller. You have to consider those overall size. I can't be driving on I-57 with a 40-foot wingspan. Okay, got to fold it up like Terrafugia. Okay, but now I'm hauling around this weight, this aerodynamics in the car mode that I don't need. Okay. And then finally, conventionally internal combustion engine powered. We're trying as a society to move away from that. Okay, greenhouse gas, carbon emissions. We're trying to get to electric. We can have a whole debate about whether that's less or more efficient. The aerospace industry has got an interesting perspective on that, about what's more efficient. But we're trying to move away from that and get out of there. So how do we conquer these things? First of all, we go to vertical flight. Okay, skip a runway. Okay, let's go straight up like a helicopter. Well, now my power requirement just went from about 1/10 of the weight to the entire weight, if you want to think about it in terms of power and thrust. Okay, now all of a sudden I got to generate 10 times more power to get off the ground. Well, internal combustion engine went from a little 100 horsepower down to 1,000 horsepower. In fact, one of the vehicles I'll show you, it uses 2,000 horsepower to get off the ground. To put it in perspective, just to get up, just vertically go up. That's how heavy it is. Okay, let's get rid of the driving. We're going to go vertical. We're going to just stay off the roads. Safety standards get a lot easier because now we can tailor them for just this. Okay. Now, is it an airplane? Is it a helicopter? We don't know yet. The safety standards for helicopters and airplanes are different. Okay. If you go through the FARs or the EASA CSs, the certification standards, they're different. We're trying to figure out as a engineering discipline, what's the right answer for eVTOL? Okay, it's not quite an airplane, it's not quite a helicopter. And then pull up batteries. Okay, this is a great idea. Tesla's doing real good things with batteries. Is it the right answer? Don't know. We're waiting to see technology to come up. This is becoming a limiting factor. And if you design a vehicle for an air vehicle or an eVTOL for about 100 nautical miles, about 50% of the weight right now is batteries. I want you to think about that. A 5,000-pound vehicle, which is roughly what we've kind of sized in our studies, that's 2,500 pounds of batteries just to go 60 miles. So that's roughly what? Here to Champaign and back with a little bit extra. Okay, not much. Okay. And then, of course, the overall size continues to be a problem and a factor. So those technologies. The current specific energy at the pack level, you'll hear these numbers that are much larger than watt-hours per kilogram for a cell. But when you put those into a pack, that efficiency goes down. Okay. Everybody remember the Boeing 787 and their battery problems? Same problem. At the cell level, they were really good. When I pack them all together in their lithium batteries, they heat themselves. And they cause problems. Okay. Here's why I'm here today. That urban environment integration. The size like we talked about. Acoustics. If I pull out of my garage and I pull out of a car right now, a car without a muffler, I'm probably going to get a noise complaint from a neighbor, right? Anybody heard a header straight off a car? It's pretty loud. Okay. If I pull out and spin up a helicopter right next to their house, they're going to be kind of grumpy. So we have to think about these acoustics, and that's where STII comes in, right? So we get this facility going. Being able to go in and run one of these near a building, hover near a building in a safe place, and go measure those acoustics. How bad are they? Are they acceptable? Are they not acceptable? Okay. Safety, of course, like we talked about, and air traffic congestion. Okay, we're talking about package delivery UAVs. Fine. If I then put in flying cars into that same airspace, you're going to be dodging stuff. It's going to be like that scene out of I can't remember which Star Wars it was, where Anakin jumps out, it's like falling through all the different levels of vehicles, right? We don't want that exactly. So how do you integrate all of this stuff? And again, out here at STII, we can start doing things like that. Put small UAVs, and if there's a problem, we're in a safe environment. So let me bring up some examples. Okay, you've got electric helicopters. I can literally take the internal combustion engine out, stick it in a helicopter, and make it work. They've done that. Not the most elegant solution. In fact, you'll see helicopters like this flying around here. This is a Robinson. And you'll see with the tall mast. Not quiet either. But are helicopters annoying? Not really. You can go to multi-copter. So I take that, instead of one big blade, I go a whole bunch of little blades. You can do a hybrid. which is the way I described it is I take a helicopter, I take an airplane, and they have a kid, right? And it's kind of both. Okay? We put them all together. You have tilt wing, tilt rotor. You hear about the V-22, all of that's long history. A lot of companies are headed this way. And then you have fixed wing vector thrust. Okay? You can take an airplane and then bend parts of the wing now and point those thrust devices in all different directions. So those 5 categories, let's talk about them a bit. Electric helicopters, loud, low frequency acoustics. That's the thump, thump, thump you hear when a helicopter goes over. Annoying, loud, it carries a very long distance. But it's not annoying to the ear in reality. Okay. The other thing is a rotor must lift the entire flight. That's not great for forward flight. All right, so let's go to distributed electric propulsion. Actually, let's set that here. There's one thing in here. You have an oh no bolt. That's the best phrase I have for it. There's one bolt on the helicopter. If it breaks, the rotor stops moving, and there's nothing you can do. Okay? So redundancy and safety is a problem here. That's why the certification standards are different for helicopters and airplanes. Distributed electric propulsion. Let's take one big rotor and make a bunch of little ones. We get redundancy. Great. Okay. But now I just made acoustics the wrong way. They got high frequency now. Attenuation's better, but it's more annoying. So there's an aerospace, well, an acoustic. There's something called PLDB, perceived loudness decibel level. Okay. That's a function of the frequency. Low frequency isn't as annoying in that weighting as high frequency. You got to be careful here. Okay. But again, rotors have to lift the entire flight. They're working that entire flight. You take the kit version, the hybrid or lift plus cruise, you're back to that large footprint because you got the airplane footprint. Okay. And the problem with this is once you're in the air, I shut the lift system down. Now I'm carrying around dead weight. It's only used for about 2 minutes of the flight, up and down. Is that the right answer? From there, you get into a tilt wing, tilt rotor. Okay, let's use those rotors in both directions. Okay. Start getting complex aerodynamics and still have that large footprint. Okay. Now you have a problem. I have to design the same power system to do 10 times the power and 1/10 the power and be efficient in both spots. How do you do that? How do I design a motor or electric system that's efficient to fundamentally different power areas? Not a trivial thing. Okay. In civil engineering, how do you do it? You have banks of stuff you can turn on and off, right? Back to that kind of distributed electric idea. Fixed wing vector thrust. Okay. This is still that large footprint. And the aerodynamics of this are a nightmare because when you turn the power on, it influences the wing. When I turn it off, that influence goes away. Power lift is a very peculiar and precarious design challenge. Each one of these has its benefits and drawbacks. So let's talk about the aerodynamics. Okay. For vertical flight, the lowest rotor loading. So if I take that rotor disc area, over the weight over that lowest value is most efficient from a power standpoint. That's why helicopters work, right? But you compromise that for forward flight aerodynamics. When that big rotor disc is moving forward, one of those blades is going near 0 speed. The retreating blade, when you're going forward, is actually not seeing much airspeed. That's a problem. If we know how to make it work, but it limits the forward flight speed. Vertical flight redundancy is a must for safety. Okay. As I said, when one of these things breaks, it's kind of over in a helicopter. That's why the safety standards are so stringent for a helicopter. You have to have like a 30G seat. So your pilot seat in a helicopter like that has to be capable of 30 Gs without breaking. That's huge. Okay. Safety standards are different. Okay. You can go to quad rotors. We've all seen that. I've been to grab one on my way out the door and I forgot. The little quad rotors, drones as we call them colloquially. Okay. If I lose one rotor, anybody have one? Anybody flown one? A little. Okay, if you lose one rotor, what happens? It falls out of the sky. that's not satisfying safety. So you see a lot of these ideas that are quads. I'm not sure that that's going to be certifiable in the long run because they have some redundancy, but not a lot. Hexacopters. So let's go from 4 to 6. They're appealing because you have that redundancy. I can lose one and still fly. But depending on the certification standards, the FAA says you have to have one failure plus a probable failure. And they're going to tell you the 2 most critical conditions, which for a hexacopter are the one that failed, the one next to it. Now I've lost control. So this is still yet to be determined. There are ways to fix this. It gets complicated. Finally, wings are most efficient for forward flight. Next, acoustics. Okay. Rotors, propellers make noise regardless of size. Therefore, frequency becomes the concern. High frequency, attenuate faster. Okay, that little mosquito by your ear gets really annoying when it's close, right? But more than about 6 inches from you, you can't hear it. If you take a bumblebee, you can hear it from much further away. Because that frequency content attenuates different in the atmosphere. What's the right answer? Do we make them loud for real high frequency so they attenuate? Not in an urban environment. Because if you're next to your neighbor's house and it's got a screeching sound, that's not going to be acceptable. Interacting rotor waves create additional noise sources. When I have propellers close to each other, you get acoustic coupling, you get acoustic multiplication, okay? Acoustic resonance. They interact with each other. That creates an additional noise source. How do I fix that? Well, one way is I duct it. I put a duct around it. Okay? If you look at these helicopters and you've seen them fly over, probably almost guaranteed to have seen this one at some point, because that's Carl's helicopter. It has a different frequency because of that ducted rotor. So what is right? Okay. It's very daunting. Right now, tilt rotor and hybrid tend to be leading. These 3 are actually 3 that have flown full-scale vehicles, uninhabited, but full scale. We're still waiting to write the regulations. And in my opinion, that hybrid lift plus cruise design are the most robust because I'm not mixing things. I'm not trying to tilt stuff. I go up, I turn the forward on, I move forward, I turn the vertical off as I go. They're very robust. You pay extra weight penalty for that. So what have we designed here? These are a couple examples of what we've thrown together. We spent a lot of time on this, I'll tell you that right now. Doing that, ducted rotors, ducted fans here. And we've also started to look at some of that open rotor. What's the right answer? We've done Navier-Stokes CFD simulations, both viscous and inviscid, to double check ourselves using SU2 and evaluated what would be the canoe design, this versus the rod design. And would you believe if you run this with the rotors open, not covered, not aerodynamic, you get a really high drag for your lift coefficient. If I take the rod based here, that's the black line. If I just close the first hole, I can actually get the aerodynamics down. That's important, right? Because if I can make the acoustics of this one better, this is the way to go. And that's hard to, an acoustic, I don't know if anybody got acousticians in here. Acoustics is a bit of a black magic art. I literally sent them 2 different things, said this get louder or quieter. They said yes. That's from a former career. I was in. But just knowing I only have to have actuation on the first one, that's a big deal. Versus having to close and make everything nice and neat and fair. We've done the full configuration CFD. So we started putting everything on. We got some hot spots, some other things we need to work on. But we're working on that problem. So most of the ducted rotors have less drag than the open rotor. That's a good thing. We need to work on some of fairing the motors a little better. The ducted rotors typically have reduced power consumption, okay, and better acoustics. Okay. As I talked about, that's things we need here with the STII is to go run these up next to buildings. Do they shake the windows? Do they break the windows? can you actually hear it inside if it's high frequency? NASA does this a lot with sonic boom, and that's where my kind of background comes from. Future work, we're looking at, again, more of that full configuration versus our empirical. We got to start varying the wing. We threw something together. We estimated it. There's room to be improved. I'll tell you that right now. Okay. Got to look at motor fairings. What happens when we lose or damage a rotor? We're going to start doing powered CFD, which is quite challenging. Forward flight propulsion aerodynamics. What's this look like when I have those rotors open and they're transitioning and they're powering up? Redesign as needed, and we've actually had a couple of prototypes flying. I'll be careful with that word. A couple versions of it. One we're still working on, and then what's next? And then start scaling up as something we could fly around, possibly STI when it's ready. Question? And I want to thank Phil Ansel and Virgil Morgan. Question? Oh, no, actually, we're waiting right at the end, right? Yeah.
Very much, Dr. Merret. We are going to save the questions until the end, so please keep them, and then we will have them at the end. Now we have Dr. Hajj. He has his PhD at University of Texas at Austin, and he is an assistant professor here. His research focuses on chemical and physical characterization of asphalt materials and designing new construction materials for the next generation of flexible pavers. So let's give him a hand and
sure. Thanks, Egeman. That works. Okay, that's working. Okay, I just forget about it. That's okay. I don't need notes. Okay, so, whoops, sorry. That's going too fast. Okay, today I'm going to talk about self-healing asphalt materials, mostly a little bit about concrete. So first of all, thank you so much for inviting me for this talk. It's really a pleasure to be here again at the Kent seminar. Really excited to share kind of a little bit of the background of just how we're getting started out in this, working in this space. So first of all, I'm working on this project with a collaborator, Professor Nishant Garg, who's also from our department. He's an expert in concrete materials. My expertise, as Egeman said, is more in the asphalt materials. So that's a little bit what I'm going to focus towards, but I'll talk about both throughout this presentation. So here's a little overview of what I'm going to cover today. And I want to start out at what's really going to be the most important is the background into asphalt, because when we think about self-healing materials, especially people in other fields, maybe in composites and in concrete world, they're thinking about what do we add to this material to make it a self-healing material. Now, asphalt's a little different. Asphalt already is a self-healing material, right? We know that asphalt heals by two major mechanisms. Asphalt heals by crack wetting, which is when you've got a micro-sized crack, molecules actually diffuse across that crack. Could be cohesive. That's generally how we think about it when we talk about the healing property of asphalt, but also could be adhesive. And this is going to be very important as we move forward. How do we heal damage that's not only happened between asphalt binder inside an asphalt binder, but also between asphalt binder and aggregate, right? Then there's intrinsic healing. Once that micro crack has been breached by the diffusion, then those two materials actually diffuse into each other and reverse the micro damage that happened, restoring somewhat of the original properties of the material. So here we go. So again, we've got a couple of different, I'm going to just make all of that show up. There we go. We've got a few different kinds of works that have been in the literature. This was really the first part of this project, was figure out what's been done before. As far as the mechanism, that part is the least researched, actually. So the differences here and how that shows up in the rheological properties, this is the least researched part in self-healing asphalt right now. Now over here, quantifying healing at multiple scales, there's been a lot of work done in molecular dynamics to look at what's happening at the molecular scale from a simulation point of view. But again, looking at the true mechanism in experiments has been kind of neglected in favor of looking at simulations of the mechanism, right? The easiest way to do molecular analysis is by by having a computer do that, right? So Then there's been studies of the binder self-healing properties. There's been quite a large number of those, and then some at the mixture scale as well. And then finally, extrinsic healing. So this is the second type of healing, and what our proposal for this project at least is focused on a lot. The extrinsic healing is when you add something to heal the binder. Now in the asphalt world, this is a little bit different from what's been done in other fields. We'll talk about that a little bit. Just to give a blanket overview, there's two main technologies that have been proposed. One is you fill a small capsule with rejuvenator or a softener, and that capsule breaks as the crack drives through that capsule. And when that capsule ruptures, that rejuvenating or softening material flows into the binder and makes the wetting and diffusion happen more easily, right? We know that the self-healing capability of the binder is directly a function of the stiffness. So you add something that makes the binder softer. This is then going to increase the healing capacity. Second mechanism is through induction heating. And this is basically where you add something that conducts heat as an aggregate to the asphalt specimen. So you can add some steel slag, for example. Then you heat you use induction to heat the pavement, and that steel slag raises the temperature of the asphalt binder. And at higher temperatures, again, that healing capacity is restored. So both of these mechanisms, what's very important and what I want to stress is that these are not creating new healing. These are just restoring the healing capability of the asphalt that already exists, right? Making the healing capacity better. Healing potential is generally increased by an increase in light fractions within the binder. So again, asphalt, for those who aren't as familiar, is a petroleum derivative. So asphalt is coming from basically the refinement of crude oil. Usually it's the bottom residue, so the heavier fractions, but those lighter aromatic type fractions, if we increase those in number, we generally increase healing potential. Which in turn decreases the viscosity. And then finally, when you have aged asphalt, stiff, brittle, oxidized asphalt, if you can add a rejuvenator or a softener, that also increases the healing potential. We did some work on that. This is from a paper with my student Babak and his master's advisor. We did look at some of that. For example, here's the healing capacity of the unaged asphalt. When we age it, the healing capacity decreases a lot. When we rejuvenate it, goes back up, right? Then you can re-age and see that the healing capacity decreases again. So the healing capacity is dependent on aging. It's also dependent on a lot of other factors, which we'll talk about in a bit. So now I'm going to talk about the microencapsulation method, which is kind of, at least initially, the focus of our project. So microencapsulation, again, the idea is you place the healing agent in a more brittle capsule, not totally brittle because it should not break during mixing and compaction. You place the healing agent in a capsule, you add those capsules to the material, and the capsule fractures when the crack is driven through it, right? You end up with something like that, releasing the healing agent into the binder. For asphalt, the goal, as I said, is to restore the intrinsic healing capability of binder so that you can close the micro cracks as they form, right? So crack forms, healing agent is released, that healing agent diffuses into the binder becomes softer, and it closes that crack on its own. We are taking advantage of the healing mechanism that already exists in asphalt binder. Now, when it comes to Portland cement concrete, we're talking about something totally different. The PCC does have actually some intrinsic healing, but it's a totally different mechanism, and it's not something that we can make happen like that. So instead, what we want to do with a microcapsule in concrete is we want to form a precipitate that has similar properties to the Portland cement that can actually increase the strength and restore that crack to something that will take more energy to fracture again. Or we have a second option. We can seal the cracks using a healing agent just to prevent water infiltration. If our strength is still intact, one of the biggest issues with concrete can be cracks allow water to infiltrate and destroy rebar, right? So the self-healing, I don't think of as just a self-healing agent in terms of restoring strength for concrete, but also it could be an in situ crack seal. That's something we're exploring right now as well in this project. So there are a couple of encapsulation methods. One is a hard shell. So that's going to be a glass or ceramic tube filled with a healing agent. Of course, this is not going to work for asphalt, right? Because if we have an asphalt material and we put a hard shell capsule in there, that's going to break when we mix it and compact it, right? So that's not going to work. Nothing brittle is going to work for asphalt. So we need to use soft shell capsules. Basically, we emulsify to allow the healing agent to be encapsulated inside a polymer coating through chemical synthesis. Here's what those microcapsules look like, and here's kind of the process. So essentially, we add the healing agent, so the rejuvenator, to the shell wall constituents, which are polymeric materials, the materials used to synthesize the polymer. We homogenize those materials to create an emulsion, right? Emulsion, again, hopefully refresher for most of you, means we're mixing two things that don't normally mix. So we use homogenization and an emulsifying agent to do that. We shear mix to agitate. So we shear mix with formaldehyde, which is one of the shell capsule materials, to agitate the mixture. And then we dry it to precipitate the microcapsules. So we end up with these microcapsules. The size of the microcapsules is almost entirely dependent on the agitation rate. Professor Nancy Sotos here at UIUC has done a lot of work with regard to the proper agitation rate to generate those, but that's basically the process that ends up with these microcapsules. Those, again, in that photo are about 3 microns in diameter. We can make them bigger again with slower agitation rates, right? Now, there are some serious drawbacks of this approach. I don't want to act like this approach is a silver bullet. Every presentation about microcapsule healing makes it seem like this approach is perfect. It's not. First of all, scaling the encapsulation is tricky, right? You have to spend all day synthesizing a very small amount of microcapsules. At the pavement scale, this is not a trivial task, right? We cannot do this. We don't have a procedure for doing this at a larger scale. Right now, this is mostly confined more towards laboratory. So that's going to be a problem. Capsules like they only work during the first cracking, right? So you crack it once, the capsule breaks, your rejuvenator is flowed out, you don't have a second chance, right? That material, if it's a top-down crack especially, is going to age again. You're going to then not have the ability later in the life to crack it again, right? So it's going to work once. Potentially, and some studies have shown that these capsules could compromise the rutting or deformation resistance, which could lead to deformation in the pavement structure. Of course, that's a problem if you have deformation in the wheel path. Due to the HMA layer, you're going to then have water flowing through, flowing in those ruts and creating hydroplaning, right? And then finally, this is probably the biggest difficulty. When you have a crack, you have a change in volume, right? You have a void. And you cannot just increase the volume available within the capsule to fill that crack, right? So you still have a change in volume, increase in volume with a crack. It's very difficult to fill that volume. This is one of the problems with the crack seal that we talked about for concrete. You cannot totally fill that volume, create volume out of nothing. They do have some ways, what they call superabsorbent polymers, that increase in volume with water. We're not doing that right now. We're focused on the capsules, but there are options, but with the capsules, it's very difficult. Okay. So now we want to think, is there another way besides capsules? So we wanted to explore all options before we go all in on this capsule idea. We're working on it, as you can see from our photos. We have some, we are synthesizing capsules right now, but we want to make sure we have some other alternatives. Remember, asphalt is already a self-healing material. If there's one thing you take away from this presentation, it's not that when we talk about self-healing asphalt, we're not talking about making something into a self-healing material. We're talking about making a self-healing material better at self-healing, right? We can take advantage of this. We know that self-healing depends on all of these factors. Self-healing depends on the binder properties, the original binder properties, the temperature, rest period, how long do we give it to rest before we load again? Aging, as we talked about, the level of loading, the damage level, and even the mixture properties, right? The properties of the aggregate and the asphalt aggregate interaction. Self-healing is linked to all of these things. It's not just one thing that causes this. We already know we can add healing agents. I showed this figure already. We know we can add healing agents to increase the healing capacity, right? There's no argument about that. Directly to the binder. So we did it here. We just added the rejuvenator directly to the binder, right? We don't have a self-healing capsule here. We just mixed it with binder. And that worked, right? For an aged binder or recycled binder, we add a healing agent, or we add a softening agent, it gets better at healing. No need for capsules. We can do that before we add it to any capsule. We also know from the literature that it works in the capsules as well to increase the healing capacity in situ. But what I want to talk about is the idea that instead of focusing on always the in situ method, can we take advantage of this? Can we just modify the binder to be better at healing and become a better self-healing material than what we can accomplish with the capsules? And that's a question we seek to answer before we go further with the capsules. So this is what we started working on. And some of our preliminary work really comes down to the work that Professor Sam Carpenter did in this center when it first opened up, because he did a lot of work to do with the fatigue of mixtures and looking specifically at the polymer modified mixtures. And there was a lot of argument, does polymer make healing better or worse? And generally, he saw a trend that if you add polymer to the mix, you can increase the healing capacity a lot, which makes sense, right? The polymer is elastic, and the polymer also has an inherent self-healing property. The polymer is like asphalt. It has an inherent self-healing. It's long chain material. Those molecules can diffuse. They're not brittle. They're not a Portland cement. They're not a metal, aluminum, for example. They're something that has that inherent healing property. Okay. So my student Babak, in his master's work, he did some excellent work looking at the influence of SBS on healing capacity. And he did see that at low levels of damage, you cannot see any influence of SBS, right, on healing capacity. And that's very important. SBS is a elastomer. SBS becomes active when you stretch it a lot, right? That's when we see its effect. So at low levels of damage, that top figure, you don't see much improvement. Then you do start to see improvement using traditional healing capabilities. I won't go into the specifics of IH, but the important thing is then when we look at RH, residual healing in the binder, the SBS actually looks to compromise the healing at low levels of damage. But as we go to higher levels of damage, you see a massive increase from the SBS versus the unmodified binder. So the SBS is key towards promoting healing. And maybe, just maybe, it can actually promote healing more than whatever's in that capsule and breaks. Or we need to start thinking about new ways to modify with other polymers as well. So our work is going to focus primarily on the polymer modified asphalt, as well as looking at the microcapsules. So that's kind of where we are right now. We did some preliminary studies of the literature to understand that polymer is going to play a key role in self-healing asphalt. It cannot be done with capsules alone. We face a lot of challenges with capsules that we simply cannot overcome, especially when we get into those higher damage levels, right? Once the cracks become a little bit bigger, once those cracks are no longer micro cracks. So our future work is going to be focused on optimizing the intrinsic healing of the binder using polymer or other modifiers to achieve greater healing than we could achieve before. There is not a lot of studies at the binder scale or even the mixture scale that focus on how can we optimize the use of polymer, especially with higher contents, to achieve greater healing. So we're going to focus on that, and we're going to compare with the healing we achieve using the microencapsulation. But probably the most important thing that's going to come out of this project, at least in the immediate implementation side, is that we want to develop an encapsulated crack sealant for protecting the rebar in Portland cement concrete pavements. And the reason that's so important is because, first of all, concrete pavements are expensive, right? They have longer lives. We need to protect the rebar at all costs. And on top of that, to protect the rebar, you don't necessarily need to increase the volume, right? I talked about that volume change that happens with the crack. You don't need to increase the volume to protect the rebar. You just need to seal the crack. You need to keep water from flowing through the crack, right? That's going to be the key for Portland cement concrete pavements. And we are working on an idea right now to do that, hopefully writing a proposal for the NCHRP idea, where we actually combine asphalt materials and concrete materials where we can be the crack sealant for their PCC pavements. So we're really excited about that work. And that's where we are right now. I want to definitely thank the SCII for sponsoring this study, and to my students, Babak, Abhilash, Yuja, and Hanan, who all worked on providing both results, preliminary studies, and kind of their impact on this, input on this work. And happy to take questions in this panel format.
Thank you very much.
Yep.
Questions for our speakers? We'll start with Dr. Merret because he's a little bit short on time.
Thank nice presentation, Professor. I was thinking that the vertical takeoff and landing concept is like very well established in military applications. You mentioned the V-22 F-35V, which has vertical takeoff and thrust vectoring. So I was thinking that are any of these major companies, Lockheed, Boeing, Bell, are they trying to invest in this market? Because it's like if it works, it's a big market that they want to like have a head start above everyone else.
Actually, no, because military side has much different requirements. The risk, the acceptance of risk is much higher for V-22. For V-22 to go down and pick up a service members or damage the vehicle or infrastructure is a lot more acceptable than having it happen on the civilian side. So they tend to stay a little bit arm's length when it comes to civilian. So they have some technologies, but again, what's acceptable on one side is not acceptable on the other. And that complicates the problem because you're right, they have good ideas, but they don't always map one to one. That makes sense?
Yeah. One more small question. Like you mentioned that you want to make the power source for propulsion like electric. So would thrust still be coming from a propeller, or is there like any other source?
No, it'd be from a propeller. In my opinion, turbo electric is a near-term solution, just like cruise ships work. I still burn hydrocarbons, but I can be more efficient with different power settings by turning it into electricity and electricity into mechanical power. We'll see what happens as batteries. Batteries are just too heavy right now. I mean, you go pull a Tesla and it's got 1,200 pounds, 1,300 pounds batteries, just batteries. Now that's a road car. Now take that times 10, and I gotta carry that around in flight. It's a tough problem. Sure.
I had a follow-up on that comment about the batteries. Do you know how quickly people in batteries are working on making them lighter? Because it seems like
Oh yes, they're working really hard on it. I think Tesla just announced they're gonna have a new cell coming out that's got like one step up. But again, you can't look at the cell number because when I put that in a pack, now we gotta have wiring, now we've got to have cooling, now we gotta have a whole bunch of electronics monitoring each cell. And if you have one bad cell and you're trying to pull and push power on it, that can destroy the whole pack. So cell to pack level is usually about a 10 to 20% penalty. So give or take a little bit. So yes, everyone's working on it. If someone comes out at 300 watt hours per kilogram, we will start seeing electric aviation really, and then pun intended, take off. So I mean, about 300 is about when we'll start breaking even. We're not always losing on that range. Anything above 300, we're almost doing better than gas.
so the designs you're proposing, are you banking on that or expecting to use on the electric or batteries?
We can do a short range like that 60 miles right now. That's not great. I'll just say that much. This goes back to the early days of electric cars where you had range anxiety, right? Plus, think about it this way. I then have to park and sit for an hour for it to charge. And that's also where the rub comes, because even if we get to high watt hours per kilogram, really weight efficient batteries, if they can't charge fast, that doesn't help us either. We actually need both. So we're getting there. There are people working on it. We'll see how fast it goes. My opinion, lithium's on the technology curve. We're starting to level out on lithium. We're going to need to really break that 300. We're going to need new chemistry, in my opinion. If you look at battery technology, it's starting to wane on the lithiums. They're really fighting for that last few percent. Go back 20 years, NiCads or nickels versus lithium. We need that next to see that they go up above.
Do you have any other questions for our speakers? Or Dr. Merret or Dr. Hajj? Do we have anything in general?
Yeah, there's a question from Angel Montero. It says, I think this is for Dr. Merret. It says, how do you predict the trend of autonomous vehicles affecting the battery technology of aircraft?
It's okay. Let's go south of green. It's supply and demand. There's a huge demand right now. It's pulling instead of supply pushing. It's driving the autonomous vehicles, whether it's cars, airplanes, everybody's begging for batteries, phones. It's really that pull, that demand is there. The technology just isn't there for airplane level yet. We're seeing cars really starting to become mainstream. Tesla's really shown us that. We'll see airplanes probably lag, my guess is about 10 to 20 years before it starts becoming mainstream, give or take. That's usually the lag. You'll see it in road vehicles before you see it in air vehicles.
Can we change? to the
Yes,
next
yes,
one?
please.
I was wondering about what you were speaking at the end about using asphalt in concrete. Not long ago, I was reviewing a paper about this, and one of the main concerns I had was that there were no uses for it. Where do you envision this is used? Or is it already used in some applications?
Yeah, I think Professor Raisler has done a lot of work. I don't know if he's online, but he can certainly talk about the uses for wrap in Portland cement concrete. That's been used for quite a while. Reclaimed asphalt pavement for those who are unfamiliar. But that's, I think, very promising. Even more promising is that I was just speaking with him about possibilities for ensuring that the asphalt used there is what we need to supplement concrete rather than just pulling wrap from any stockpile. So we've talked a lot about that. But from our scale, we're thinking way smaller. We're thinking micro scale. So we're thinking about asphalt at the micro scale, how we can stop water infiltration, right? We know that concrete, the biggest problem is not the biggest. I can't say that, I'm not a concrete person, but one of the biggest problems in concrete is water infiltration, right? It damages rebar, it gets into air pores and freezes and causes expansion, which causes cracking. So water infiltration is the biggest problem. We know that asphalt is a hydrophobic material. We imagine that we can use asphalt in part to prevent the infiltration of water into the concrete structure, but that's going to be at a much smaller scale. I would say stay tuned for more details about that, because that's what we're working on now, is how to do that, but way smaller scale than what's been done in the past. You saw our capsules are 3 microns, right? So these are totally different. I mean, this is a small scale for asphalt, let alone concrete, right? This is smaller than mineral filler. So, yeah.
So I had a follow-up question. For those capsules, now, do they change the properties of the material? Like does it make it like more brittle or more ductile?
Yeah, one of the big issues, I think I mentioned that the capsules generally are found to decrease rutting resistance when you get to the mixture scale. This is because essentially they are kind of a filler, and they're not a very high quality filler compared to a hydrated line, for example. So these capsules do increase your filler content, and they can lead to rutting susceptibility, especially rutting we're usually measuring in a wet setting, right? Moisture with the Hamburg test. So generally we do see some issues in the rutting domain and the moisture resistance. So those need to be resolved before we can deploy this on a massive scale. But as I mentioned, it's not scalable to date. So that's something we're focusing on how to improve that. Of course, there are ways you can improve rutting resistance, you can improve moisture resistance, but those almost always come at the expense of cracking resistance, which if you compromise your cracking resistance to use a self-healing capsule, that defeats the purpose, right? So these are the challenges we face. I mean, I frankly think that the people who have done this work in the last 10 years have made it sound like they found a catch-all solution without ever thinking about scale or thinking outside the box of cracking. So that's what we're trying to avoid in our project.
Yeah, I have a follow-up. Oh, sorry.
Yes.
Yeah, go for it.
I was just curious about the proportioning. So would these capsules be replace the volume which would have been filled by the filler, or do they have another criteria for incorporating them into the mix?
Depends on the size. Depends on the size. I mentioned we can manipulate the size by agitating at different rates. So depends on what size we want to use. But in general, I hesitate to say they're a replacement for filler because, as I mentioned, you cannot have a good mix without the mineral filler, at least for a dense graded HMA, for example, what's generally at the bottom of our pavement surfaces. So I don't think it's a replacement for filler, but I think essentially you're adding filler. There's no question, at least until you get to the stage where capsules start breaking. And then your mix design changes a little bit, right? When the breaking happens, you no longer have these capsules there. You have rejuvenator flowing out. You've actually added a little bit of liquid content, right? I won't say asphalt content because the rejuvenator is not asphalt, but you've added to your overall liquid binder content, right? So yes, there's definitely something we're considering is how to incorporate it in the standard mix design.
So that's like all the time we have for today. We'll thank our speakers for their talks, and then we'll see you all in next week.